I'd like to talk about joint work with Paul Dütting, who's also here, on posted pricing and profit inequalities with inaccurate priors. And good morning. So probably having seen these previous talks, you may already, reading this title, have an idea of what our paper is about. Nonetheless, let me give you one example you can think about. So in this setting, we would have n buyers arriving one by one. We would have m items, which are these two great cell phones. And then at each arrival, we have to decide which items to assign to the buyer that just showed up. And our goal will be to maximize social welfare. So I now designed this in a way that I set just item prices statically, and a buyer just takes whatever he prefers, or she, giving these prices. So this guy, for example, has zero utility when he buys anything, so, well, he doesn't take anything. So this lady now, well, she could take the first item, would have a utility of -2, or the second item, then she would have a utility of 6. So 10 minus 4, so she takes the second item, and then we've collected already social welfare of 10. But that item's gone. This guy takes the first item, so that item is also gone, and now this lady shows up. Well, she cannot take anything, although she would have really high value. So our social welfare would be 10 plus 5. Importantly, these prices are just means of coordination here, but I'm not actually interested in the revenue, I'm interested in the social welfare. And that's actually a setting that people have been studied before. Nick alluded to this. We might now choose item pricing, bundle pricing, change prices over time, and something people have asked is, well, how good are you compared to what you could do optimally? And what is a standard setting to analyze this uncertainty? Well, you have now these buyers who have different valuations, V1 through Vn, and they arrive in order 1 through n. And, well, in advance, we don't know these valuations. We only know the distributions, the probability distributions they are drawn from. So Vi is drawn from distribution Di independently, and D1 through Dn are known beforehand. Our question was now, well, what if we are in this setting, but we don't know these priors, these distributions in advance, but we only know them approximately? So let's make this a more precise mathematical question. So these buyer values are still drawn from distributions D1 through Dn, but in advance we define prices only based on distributions D1 tilde through Dn tilde, with a property that the distance between di and di tilde is small, is less than epsilon for all I. So what does this even mean, the distance between two probability distributions? Well, that's our assumption that this distance is small, and we have to define distances between probability distributions. And fortunately for us, we don't have to do this because that's what people have done before, and there's not just a single notion of a distance between the probability distributions, but there are many. I'm listing 5 here on this slide. And in the following, I'd like to only talk about 2 of them, namely the Levy metric and the Kolmogorov metric, because for the following, I'd like to focus on the case that I have a single item which I want to allocate. Why that? Because then actually a probability distribution can be easily described in terms of the CDF. So let's talk about this Kolmogorov metric. What is the Kolmogorov metric between 2 probability distributions? So you might now have just some probability distribution over a real number, which looks like this. So this is the CDF of that distribution. And another distribution is now within Kolmogorov distance epsilon, if this CDF has only at most an epsilon vertical distance to this CDF at any point. So any CDF that you could now put between these 2 red lines would be corresponding to probability distribution within Kolmogorov distance epsilon. Okay, and you may realize that if the slope is very high, then actually you don't have that much space here. The Levy metric is quite similar, but what you now also allowed is horizontal shifts. So you're not, now these red lines, of course, are further apart because they're also shifted by an epsilon horizontally. And you may realize you now have much more space. So the distances are generally smaller in the Levy metric because, well, this respective epsilon that you need is smaller. So what do we find out? Well, let's now still talk about this single item setting because people have studied this intensively. And what could you do? Well, what is a very fundamental technique that you could use to deal with a single item setting? Well, you could choose prices P1 through Pn so that you maximize social welfare, which you compute by backward induction. I'll tell you in a minute how this exactly works. Or something else that you could do is just choose one static price, which is just choose one P so as to maximize social welfare. Whoever beats this price first gets the item. That's just a very simple one-dimensional optimization problem. Or in the context of proving profit inequalities, people also have considered suboptimal policies, such as, for example, choosing a price so that the item is sold with probability exactly a half, or choosing a price which is equal to half the expected maximum value that somebody has for the item. So these are the standard techniques to deal with a single item setting. And what we were interested in was how do these techniques actually, how robust are they if you now use inaccurate priors? So if your distributions are only close within some probability distribution. And as it turns out, it really depends on what technique you're applying. So these optimal dynamic prices, they are robust. And also this balanced price, this last one, this is robust with respect to the deviations in the Levy metric, whereas the optimal static price and this median price, they are not robust. And maybe let me first give you an idea of what can go wrong. What is it that can go wrong? Well, I'm now drawing the same picture with the Levy metric I had before. And now suppose you want to adjust the price so that your item gets sold with probability exactly a half. And you do this with respect to this black line. But now the actual distribution might be one of these red lines. And you suddenly realize, well, actually, your probability might be as big as almost 1 or as small as almost 0. So rule of thumb is whenever you want to adjust, choose prices so as to adjust probabilities, this can go terribly wrong. But not everything works this way. For example, this backward induction approach doesn't work this way. You don't actually adjust probabilities here. And let me give you an example of how we work on this one. So how would you compute the optimal dynamic prices so as to maximize expected social welfare? Well, that's actually pretty easy. The last guy, well, we can, the item has no value if he doesn't get it, so he has to pay 0. And anyone before that has to pay how much? It's the expectation of the following random variable, the maximum of the following bidder's value, and that buyer's price. And what now? And what we can show now is the following: that if now for every I, the Levy distance between the actual distribution the buyer's value is drawn from and the prior we are using to define these prices is at most epsilon, then, well, the expected social welfare, if you use these prices for d tilde on D, this is at least the expected welfare of the optimal prices if you actually use the actual distributions on these, and the buyers also came from the actual distributions, minus some error term, which is for n epsilon. And this bound is actually tight in the sense that except for this for any epsilon, you cannot do better. So it will be this linear dependence on n. So how do you prove such a thing? Well, we use a consequence of Strassens' theorem, which is the following, that if the Levy distance between two distributions is small, then there is a coupling. What does this mean? Well, there is a probability distribution now over pairs, Vi and Vi tilde, such that the marginal distribution of the first component is the first distribution, Di, and the marginal distribution of the second component is Di tilde, with the property that the expected difference is less than 2 epsilon. And now we can make use of this. So once again, this is how we would define prices if we knew this, if we used the actual distributions the buyer values are coming from. And interesting thing is, the price that a hypothetical 0th buyer would have to pay, this is exactly the expected social welfare that we're getting. And then, what are we actually doing? Well, we're defining now the prices with respect to these inaccurate priors. So these prices P tilde, which are just defined the same way. And now, well, if the buyers were also drawn from that, well, from the inaccurate priors, then we would get actually the expected social welfare would be the price of the hypothetical 0th buyer. So if you combine this with this coupling, then what you actually see is, well, the prices are close, and because you have this, because the price of the 0th buyer would actually be the expected social welfare, you also have that the expected social welfare with respect to D tilde is close to the expected social welfare with respect to D. So this is what we showed, but this is actually not what I claimed before, because this is now, assuming actually that the buyer values are drawn from the same distribution that we used to define prices. But using very similar techniques, which I'm not showing here because it would require much more notation, you can actually also show that, well, if you now change the distribution the buyers are drawn from, you also lose at most some 2n epsilon. So in combination, you have what I claimed, that the expected social welfare when the buyers are drawn from D, but you defined the prices with respect to D tilde, is at least the optimal social welfare that you would achieve minus 4n epsilon. And as I was saying, this bound is tight, so we have an example for every possible epsilon that you cannot do better, except for this 4. I think in our paper it is a third or so in our lower bound, but you need this linear dependence on n. So in this talk, I'm focusing on the single item setting, but actually our paper is more general than that. More generally, we can talk about multiple items or matroids or whatever. This doesn't actually matter. Any general allocation problem we can talk about. But if you have, for example, multiple items, you will generally have multivariate probability distributions. And then you have to use actually other probability metrics, such as, for example, the Prokhorov and the Wasserstein metric, but generally the approach will be similar. So the positive results for the respective optimal policy via backward induction also just carry over. And then for the balanced prices approach, which used have the expected maximum value, the thing is, the prices may actually eventually be very different, but the guarantee is robust. So it may actually turn out that if you use these inaccurate priors, you will get entirely different prices, but the point is, whatever you proved to be the guarantee that these prices have, this is still more or less true. More or less because you lose this epsilon terms. So What I've told you today in my talk is when you are close with respect to the Levy-Prokhorov-Wasserstein metric, then the robustness certainly depends on the technique. If we've seen an example where actually we are robust, other examples are not robust, general rule of thumb would be that if you want to adjust probabilities, that can go wrong. If you only talk about expectations, just because of this coupling argumentation, then things will usually be okay. Other metrics are, for example, the Kolmogorov metric, which I also talked about. There it's actually interesting that any price-based policy is robust. So you might choose a policy in a weird way that it does not depend on prices, and that may fall apart. But if it is based on prices, meaning it defines thresholds, then it will actually be robust. And also, there is the total variation distance, I guess some of you have heard about. Well, that is actually a pretty strong guarantee for which, well, actually never anything goes wrong, because with really high probability, you just observe the same on both sides. And this also means in our case that any policy is robust. So how could one proceed from here? I think one interesting follow-up question is to consider other objectives. As I was mentioning, we only consider social welfare as the objective in this paper. And you could also consider revenue, or actually, I think you could apply these considerations on any paper that you see in EC, which assumes some prior distributions. What if the priors are only inaccurate? This question makes sense, I think, in many settings, even beyond profit inequalities and posted prices. Or one other question might be, what if I wanted to design a mechanism already having robustness in mind? Because our approach so far was, well, actually, this mechanism proceeds as if these were the actual distributions the values are drawn from. What if now the mechanism is actually aware that these might be inaccurate, and then you might want to work in a way that you would do it in robust optimization. There's also a different paper on this for a different goal I'm not talking about here, but that's something you could also apply to this, or actually any other setting in which you assume prior knowledge of distributions. So that's all. Thank you very much for your time.